algebras, a key idea in that of the spectrum of an element. So that A is a unital algebra with identity E. Okay? At the first, let me begin with this definition. Let us first look at the spectrum of an element in a Banach algebra. The concept generalized that of the eigenvalues of a matrix. Okay? Definition: let A be a unital algebra and let A belong to A. The resultant set of A is this set. Row A of A equal to the set of all complex numbers such that this element be invertible in A. Okay? The set of all Z such that Z EA minus A be invertible. Now the spectrum of A, denoted by this notation sigma A of A, is the complement of row A in C, so that the spectrum of A equal to C minus row A. Row A is the set of all complex numbers such that ZE minus A is invertible, and sigma A is the complement of row A. Okay? The resolvent function of A is this function. Resolvent function R by the index A maps Z to this inverse. Please note that this inverse is exists because Z is a function from this set, so that this element is invertible, and we have this element in A, and this is an invertible element in A, so that the domain of this function is row A. Okay? So in this discussion, A is a unital Banach algebra and A is an element of A. We can write if then row A of A, or simply we can write row A, okay? Row of A, the set of all complex numbers such that ZE minus A is an invertible element in A. So that this is a subset of complex numbers, okay? And Roosevelt functions by this notation row A, okay, from row AA to the invertible element of A as a subset of A equal to or defined by row A of Z equal to ZEA minus A inverse. The inverse of this element, because we know that this is an invertible element. Okay? LA. Yes, students, do you have my voice? Don't have, okay. So that this is resolvent function of A or by the index A by this function rule. It is not that this function is a function from this set, and this set is a subset of complex number, okay? This set is a subset of complex numbers, and the resolvent function is a function from a subset of complex number to or Banach algebra A, and to this subset of A. Okay? Usually we write row A for this. Okay? We can omit this capital A. We shall use the following easily checked identity for each Z and W. In row A we have this equality. Let me write this for you. For each Z and W in rows in row of A. We have this equality. Row A of W minus row A of Z equal to Z minus W, RA of W multiplied by RA of Z multiplied by RA, okay, RA of Z RA of W. So that resultant function have this property, and we have this equality, and its proof is easy, because for example, if we write this RA of W minus RA of Z, this is equal to W multiplied by EA minus A inverse minus ZEA minus A inverse, okay? Now we can write this equal to WEA minus A minus 1 multiplied by EA minus EA multiplied by this ZEA minus A minus 1, okay? We multiply EA from this element and EA from this element at the left, okay? But this is equal to WEA minus A minus 1 multiplied by ZEA minus A multiplied by the inverse of this element, the inverse of this element. Please note that we multiply this, and this is equal to EA, okay? This equal to EA. This multiplied by its inverse minus, instead of this EA we write WEA minus A inverse WEA minus A and multiplied by ZEA minus A inverse, so that we write this element, and we know that this is equal EA. Okay, this is equal EA2. EA and EA. We write this instead of this, for example. Okay. And the last term is equal to W EA minus A inverse multiplied by ZEA minus 1 minus WEA minus A, and finally multiplied by ZEA minus A inverse. Okay, if you multiplied this object to each other, we have this multiplied by this multiplied by this, and this is the first element, and second this multiplied by this multiplied by this. So we have this equality, but this parenthesis equal to ZEA minus WEA, because this A with this A can be omitted. Okay, so this is equal to WEA minus A inverse ZEA minus WEA. Let me write this parenthesis and multiplied by ZEA minus A inverse, and it is trivial that this equal to WEA minus A inverse multiplied by Z minus W multiplied by EA and ZEA minus A inverse. But this is an scalar numbers, and we can write at the first Z minus W and EA multiplied by these elements equal to itself, so that this is equal to the inverse of this element multiplied by the inverse of this element, ZEA minus A. Okay, and we have this equality. The Rule function of W minus the Reuben function in A of Z equal to this multiplication. This is equal to Z minus W okay. L of W, L A of Z. Because this is LA of W, okay, and this is LA of Z. And also we have this inclusion. Suppose A is a Banach algebra and A belongs to A. It follows from theorem 1.2 that we have this inclusion. Let me write this for you. Sigma A for any element in A. Sigma A is a subset of this set, the set of all complex numbers, such that absolute value of Z is less than or equal the norm of A, okay? And its proof is easy, okay? If Z belongs to sigma A, you can consider two cases. If Z equal to 0, then we know that Z equal to this set. Absolute value of 0 equal to 0, and 0 is less than this, so that 0 is an element of this set, okay? But if Z is a non-zero element, we know that Z is A minus A not invertible, okay? we consider Z in the spectrum of A. And so we can conclude that EA minus the inverse of Z multiplied by A is not invertible. Okay, we multiply this by the inverse of Z. This is not invertible, and this shows that the norm of this element must be greater or equal 1, or equivalently this must be less than or equal the norm of A. For this we can write you know that the inverse of Z equal to 1 divided by Z, because Z is a complex number and we consider Z a non-zero complex number, and equal to the absolute value of these complex numbers multiplied by the norm of A, and this is equal to the norm of A multiplied by absolute value of Z. Okay, and we know that this is greater or equal 1 if and only if we have this inequality. Okay, and also for this application, please note that by this theorem 1 4 2 part 2, we prove that the set of all B in A such that the norm of EA minus B is less than 1 is a subset of invertible element in A. Okay, so that if B belongs to this set, B must be an invertible element. Equivalently, if B not belong to invertible element, then B not belong to this set, so that this norm must be greater or equal 1. Okay, no, this element is not invertible, so that EA minus this or this must, the norm of this element must be greater or equal 1. Okay, greater or equal 1. So that we have these two observations. For example, if we denoted these two by a star and double star, this holds by a star and this holds by double star. So we have this property. The spectrum of A is a subset of this set, the set of all complex numbers, such that absolute value of Z is less than or equal the norm of A. Dear students, do you understand these proofs and these definitions? It is easy or difficult? Let me write some sentences for you. I don't know. You follow this or not? Allah Hastar Barahin, dear students.
هل حق البراهين.
Now we can define the spectral radius of an element of a Banach algebra. Let A be a unital algebra and let A belong to A. The spectral radius of A is this spectral radius, okay? In Arabic you can say spectral radius. نسب القطر الكيفي يحتمل. The spectral radius of A is these real numbers VA of A, or many books denoted this by R of A, okay, denoted by RA. In many books denoted by this, or VA equal to the supremum of all absolute value Z, such that Z belong to sigma of A. The supremum of all these real numbers, so that this, or by our notation, this is a real numbers less than or equal the norm of A, because all of this is less than or equal the norm of A by this inclusion, okay? The element A is called quasi-nilpotent if this spectral radius equal to 0, so A is quasi-nilpotent if this set consists only zero element, because if this is equal to 0, this supremum is 0, and so all of this must be equal to 0. All of this must be equal to 0. So that Z must be equal to 0 and the spectrum of A must be 0 only, or must be empty set. If this is equal to empty set, this supremum is 0 again. The element A is quasi-nilpotent if the spectral radius of A equal to 0. And the set of all spectral radius, the set of all quasi-nilpotent element denoted by Q of A, for example. Q of A. Q of A. The set of all quasi-nilpotent elements in A. But you know definition of nilpotent element. A is called nilpotent whenever for some n, A to the power of n equal to 0. And you can check that any nilpotent element is a quasi-nilpotent element, okay? Any nilpotent element is a quasi-nilpotent element. Please prove this. This is easy to check. That we have these properties, and also for any linear map from Cn to Cn, you know that bounded linear function from Cn to Cn equal to the set of all linear functions from Cn to Cn, and this is equal to the set of all n times n matrix, n times n complex matrix. Now it is easy to check that the spectrum of the matrix T, because all of this T is an m times n complex matrix. The spectrum of this matrix is the set of all eigenvalues of T. Please prove these two proposition. Okay, this is whole. I have two exercises, 1 and 2. Let me write this for you.
يرجى إثبات هذين كتدريبات.
Okay.
يرجى ملاحظة أنني أخصص 8 درجات من امتحانك لحل التمارين والعمل الصفي. يرجى ملاحظة أنني أخصص 8 درجات من امتحانك لحل التمارين والعمل الصفي. الترتيب والحضور في الفصل هو جزء من عمل الفصل.
And also we write this that
لسوء الحظ حضور بعض الطلاب غير منتظم على الإطلاق. لسوء الحظ حضور بعض الطلاب غير منتظم على الإطلاق. من فضلك تعال إلى الفصل في الوقت المحدد. قل هذا لجميع الطلاب.
Okay. And also we have this proposition for any continuous function in omega, for example, sigma of f is equal to f of omega. The range of omega and the spectral radius of f equal to the subnorm of f on omega, so that the only quasi-nilpotent is in C of omega equal to 0. It is not that let me explain this for you. This is an easy exercise for you. Let f belong to C of omega, so that we will prove that the spectrum of f equal to the range of f and the spectral radius of f equal to, so that v of f or r of f, v of f equal to the subnorm of f on omega. For this, please note that if z, for example, belong to the range of omega, then z minus f is not invertible invertible because we know that this function is zero at because if z belong to the range of f, then there exists an element in omega such that z equal to f of t. This shows that z minus f of t equal to z minus f of t equal to z minus z equal to 0, because z is a constant function z, okay? So that this function is 0 at one point, so that the inverse of this function or this is not exist, okay? So that z is in sigma of f. Conversely, we have if z belong to sigma of f, then z must be belong to the range of f under omega, and it is very trivial because if z not belong to sigma f, z minus f is not invertible, in this space, okay? So that this must be 0 at one point. There exists an element such that z minus f of t equal to 0, or equivalently z equal to f of t. This shows that this z must be belonging to the range of f. This is the proof of this, okay? And so v of f or r of f, the spectral radius of f equal to the supremum of all z such that z belong to sigma f. This is equal to T supremum. All z such that z belong to f of omega, because we know that these two are the same, and this is equal to the supremum of all f of t, for example, such that t belong to omega, and this is the supremum of norm of omega of f on omega. So we have this equality 2. And finally, it is very easy that the only quasi-nilpotent in this space equal to 0, because you know that an element is quasi-nilpotent whenever the spectral radius equal to 0. Okay, the spectral radius equal to 0, and if the spectral radius equal to 0, let me write in this, spectral radius equal to 0 equal to the subnorm of f equal to 0, and this is equal to f equal to 0, so that q of c of omega equal to only 0 constant function. 0 constant function. These two holds from this equality easily. Okay. Okay. Now we have this proposition. Let me express this proposition in the next session, tomorrow inshallah. Dear students, next session. Okay. Thank you very much and goodbye for now.